Our first speaker is Professor Deirdre Shoemaker from the Center for Relativistic Astrophysics, and she will be followed by Professor Laura Cadenati, also from the Center for Relativistic Astrophysics. And they will be talking to us tonight about general relativity. This is the 100th anniversary of general relativity, and we just have a brand new awesome statue out in the quad you may have walked by, and so we hope you will learn something tonight to help connect you to that statue and to physics. If you have questions at the end, we will pass around the microphones and you can ask questions. If you don't get a chance, once the talk is over, you can come down to the front and meet with the speakers. All right, let's get started.
Hey, wow, is this working? All right, am I on? Probably. I'm pretty loud without a microphone, so go like this if it's horrible. So hey, obviously we're really into Einstein here, our cute little Einstein statue, and we're going to talk about one of the three equations on the book. But before we do, to get a sense for where we are in the audience, well, if Ed will do that more often, that'd be fun. Just dance around.
You forgot the pre-show.
I'm not ready.
Oh.
Well, it could be good. They'll sleep. No sleeping. All right. What does relativity mean to you? Hard equations, sure. They have rumors. Anyone want to answer? No, it's just like class, but there's hundreds of you. If someone's waving, he doesn't want to answer.
His hand up right there.
Oh,
yes.
yeah. Go ahead. What does relativity mean to you?
It makes GPS possible.
I know, I like him. It's like my practical application. Yes, sir, it does. We will see that in a second. Anything else? No? No sci-fi fans? Yeah, back there in the gray. Yeah, different speeds for different observers. We'll talk about that too, without equations. I'm not that mean. There's a quiz. There's no quiz. At the end of this, that would be bad. Anyone else want to volunteer? Yes, sir.
I'm not sure where I am.
You're not sure where you are? That's the Heisenberg uncertainty principle or relativity? I'm not sure. Sure. We can use it, though. All right. So here's what I thought it might mean to some people. Sorry, Carl. The artist is in the front row. She's going to kill me. She's like, never send Deirdre images that you make. She painted this image, and obviously I like it. The point here is we all recognize that face, don't we? It's so funny how a physicist could be that iconic, his image, that a group of people who would probably not tell you that their favorite subject is physics, especially introductory physics, although Dr. Greco's the best, right, at teaching that, but we still all recognize this face. We also might recognize this. It's what I grew up watching, the reruns of the original Star Trek. I wasn't actually watching the original Star Trek. Anyone know what it was powered by? Dilithium crystals, and the next generation, what did they use? Right? Warp drive. Dilithium crystals, warp drive. So they would curve space-time to get themselves to move fast, right? So this is one way that we think about relativity. It's another. Anyone see this movie? Interstellar. So a relativist from Caltech, they have all the fun, was one of the executive producers of this movie. And this image is of a wormhole that, of course, they use to travel to a distant part of the galaxy where there's a gigantic black hole, which we'll talk about a little bit later. And this image is actually pretty accurate for what curved space-time looks like if you were to go through a wormhole. Now, full disclosure, we don't have any wormholes. We can't keep them open with the physics of matter that we know of, but they sure are cool looking. So what is, whoops, I can't really control this. Okay, what is Einstein to an astrophysicist? It's such a long word, it's hard to say a lot. But what do we think of? For us, we see it as something that's driving modern astrophysics. So I'm not going to spend too much time, unfortunately, on cosmology and expanding universes, although we do have another faculty at the center who works on cosmology. But it was one of the big solutions to Einstein's equations of general relativity is cosmology, and how is the whole universe forming and expanding. My personal favorite, black holes, is one of the solutions of Einstein's relativity, so I'll talk about them. This is a black hole image, the image of the way a black hole will distort the light we'd view from the Milky Way galaxy. So this is if you put a black hole between us and the Milky Way, this is what you would see. So you see, you can't see in the middle, obviously, black hole, but you see the light from the full light spectrum of the entire Milky Way. You still can see it. It's just distorted and coming around the black hole because it curves light. And my colleague, Laura Cadenati, will talk about her favorite thing, gravitational waves. in a few minutes. So here it is, my one slide of Einstein's best year of his life. He wrote 5 papers. I wrote down 4 of them up here. Anyone go to the Einstein statue talks? A couple? Oh, Paul, you'll know where I got these from because I stole this slide from Pablo Laguna. You'll recognize far too many, so you might want to escape soon. So it just was an amazing period of time. If, as a physicist, or I think any scientist, even a small part of one of these papers would have been enough to make a career, let alone all of them. But what I'll focus on is this last one, special relativity. So the photoelectric effect got him the Nobel Prize. Brownian motion is super important in many areas of science and engineering. E equals mc squared, one of the equations in the book of our new statue. Special relativity is where we'll focus. In fact, I'm going to focus on general instead of special, because it is not 2005, right? It's 2015. And from special relativity, you get those cool effects we were talking about. I don't know your names, so the people who answer, but you know the cool effects of time dilation and length contraction that you learn in class. But also he realized that all the natural phenomena he could be discussed in terms of special relativity except for gravitation. And that's why we need a new theory. So here it is. It's kind of wordy. I apologize. I love this because how dorky are you that your happiest thought is this? I like it. I like that. We should embrace that here. So a translation of what Einstein's happiest thought was that he realized that a gravitational field only has a relative existence. If you thought time was bad enough, now we'll take away gravity. Because for an observer freely falling from the roof of a house or whatever you want to jump around on, if you jump from the roof of a house with, not a dog, because that seems mean, with a stuffed animal, and you throw it, I don't know what you do. Okay, you and your dog jump. There's no easy way to do it. And as you're falling, you look at each other. It seems like there's no gravity until you hit the ground. The normal force is what kills you, right? So it's as if there's no gravitational field. And what Einstein did, so this is that scenario. I'm in space, far from any stars. I don't have a window. I'll feel the same as if I'm freely falling towards the Earth. Interestingly, if I put that elevator with this goofy Einstein on the Earth with no windows, he could conduct an experiment like dropping something and conclude, oh, I'm on the surface of the Earth. I understand physics enough. But if I stuck that same elevator in a rocket and accelerated it at 9.8 meters per second squared, if he conducted that same experiment, he'd come up with the same results. And he would think, even though he's Einstein, that he's on the surface of the Earth, despite being out in outer space. So this connection seems so simple. And it's amazing how much easier it is to understand relativity if you understand this principle of equivalence. Because it's a lot easier to calculate things in an accelerating field than on the surface of the Earth. So the reason why it's called general relativity is because Einstein saw this as a generalization of the Galilean principle of relativity. So let's get a little more modern. Here's our book. This is the equation on the book. Physicists today tend to write it like this: G mu nu equals 8 pi t mu nu. See, relativity is easy. Looks a bit like a fraternity or a sorority party. It's not a problem at all. I don't know why you guys are worried, but it's got a lot in there. It's true. They're the hardest equations to solve, I think, on a computer. But what it tells us is it tells us that space-time curvature, this grid that as we like to represent it, tells matter how to move. So if this were the sun, it tells the Earth to go around the sun instead of out in a straight line. And matter tells space-time you should curve like that. So they're coupled. And it represents 4 dimensions of space and time, and they're nonlinear and messy, but you don't have to solve them. I do. So we're okay. So let's go on a little further. One of your favorite consequences of relativity was this time thing that seems really cool. So I also stole part of this slide from Pablo Laguna, and then he's the Jose Maria person. So here we have a rocket with Maria shining light. She's going to receive the green pulses from Jose, and Jose is going to receive, Jose receives the green pulses from Maria, and Maria receives the blue pulses from Jose. And you ask yourself, if your friend was at the top of a rocket shining light down at you, would you expect you to read different clocks? If you clock the pulse reaching you, is there any expectation it would be different? Probably not, right? Except we tell you. So the answer here is that someone at the top of a building ages more than someone in the basement, is the easy way to think of this. So where you are in a gravitational field affects the way time ticks off. And if you think of your heart as a clock, it's similar. So we can get that same effect, and it's easier to think about. If you think about this rocket as accelerating, you could probably believe that this is true because, of course, as that light front is going down, the rocket's bottom, Maria, is accelerating towards it. So she reaches the signal faster and faster as Jose shines the light. So that's how we use the principle of equivalence to make it easier to understand a concept that's so hard to understand on the surface of the Earth. Why would astronomers at the top of the building be older than the experimentalists in the basement? And this is how we do it. But there's another consequence, which comes from special relativity, which is speed. So if we take this rocket and have it moving at a uniform speed, I have to take Jose out of the rocket. I put him in a suit, so don't worry. Because if they're both in the rocket, they're not going to see an effect because they're moving at the same uniform speed. It's different than when they were accelerating with respect to each other in the same rocket. So now Jose and Maria will also disagree about time. And this time, the person moving will appear younger than the person holding the clock and standing still. So if you move fast, you might say you age less. So you have to be low gravitational field and moving quickly if you want to be younger than somebody doing the opposite. That's the plan. Okay, so gravity. We have these two cool effects. Somebody, who's nameless, so sorry, about GPS. We have these mundane effects because of this really fantastic concept of curved spacetime. The fact that matter and energy tell spacetime how to curve, and spacetime tells matter and energy how to move. We have apples falling. That's pretty mundane, but it also causes this beautiful tidal disruption that we'll see in a second of a star being eaten by a black hole. Same stuff, just gravity. And it also works with your GPS and your iPhone. So if you did not correct for the way that time changes depending on a gravitational potential and the speed of the satellites with respect to your receiver and your phone, you would lose 45 microseconds per day from GR and 7 from special relativity. And you see how the signs are different because we notice that that depends on what you're doing, what the signs are. So you'd lose about 11 kilometers a day, so you would certainly not make it to your plane on time if you didn't correct for general relativity. So let's get a little deeper in black holes, because that's the cool part, I think. Anyone see this kind of image before to describe a black hole? Yeah, right? Like this, I call it a trampoline effect. One of my kids is bigger than the other, so I used to always pretend he was the black hole, and he would curve the trampoline, and the other little kid wasn't as big, and he'd fall towards him. It wasn't nice, I know, because you know those kids. So one's a 7th-year senior. He's not here. I can make fun of him. So what we have here is a solution of those equations, g mu nu equals 8 pi t mu nu. The simplest one you could think of, even if you're in a trench in war, like Schwarzschild was, obviously you doodle. You doodle that. Let's take the spherically symmetric solution. Let's make it time independent. Get a solution. This solution was something nobody liked. Einstein and Oppenheimer, big, powerful guys, very uncomfortable. Because it said that if you could collapse matter all the way down to a point, or really to a region where nothing else could support it, you would reveal an actual physical singularity. This was before we knew about the Big Bang, so we have 2 physical singularities. And they just thought that that was not a possible physical reality. But this is what we have. So here is just for fun. We're so popular in the media these days that physicists like to show Big Bang theory. So don't jump into a black hole, true story, right? So they are ubiquitous in the universe, as we're going to find out, but, and in popular culture. So it is true that black holes have this sense that nothing can escape them, and that is true. You have to go faster than the speed of light to escape the gravitational pull if you're within the event horizon of a black hole. Okay? We call this spaghettification. It's a very fancy word. I think I spelled it right. It means the just tidal forces. That if you're approaching a black hole, if you get too close, even before you hit the event horizon, the tidal forces your feet would feel compared to your head, if your feet first, would cause you to stretch out. And also, there's a lot of information available at black holes. If you fall into one, don't struggle. You'll die faster. It's all good advice. Don't want you to be unprepared. So, black holes. They sound really cool, but are they just figments of bored astrophysicists' imagination, or are they actually part of our universe that we deal with? So the truth is that we consider big stars, or how we form stars in the universe. And if you play with how much the initial mass of that star is, depending on its life cycle, its details, it actually has a path where they do form a black hole when they run out of fuel and basically die. So they can become a few different types of stars. There are others up here if they're low mass, less massive than our sun. Our sun will not become a black hole or neutron star. It's too small. But something 2 to 3 times the size of our sun or even bigger could become a black hole. So there's this easy path to form a black hole. And here is a different kind of black hole. This one would be a little bigger than the size of our sun. This one could be like gargantuan, 1 million or 1 billion times the mass of our sun. And we believe these lurk in the middle of our galaxies. Most galaxies seem to have one. So let's look a little deeper at these things. So I've used this joke too often. Probably even some of you have seen it if you hang out with me too long. But I like the fact that we're all wearing lab coats. I don't know why an astronomer would be in a lab coat and get dirty. I'm not sure. There's no chemicals in astronomy. And they're looking at this picture they've taken with the telescope of a black region of a black hole. So it's black and it looks like a hole. I'd say it's a black hole. Not the way it actually happens, right? So how do we say, if we tell you, well, we think black holes are everywhere in the universe, why do we think that? Well, it's because we can see the partner dancing with the black hole. We see matter falling into it. It gives off a lot of energetic phenomena, and that's what we're detecting, not the black hole itself, despite the beautiful images we make up in popular culture. So it can be small, like this image of a 10 solar mass black hole eating its companion star, or it can be 1 million times like the one in the center of our galaxy. This is not a real image, but it's beautiful. So this is what it looks like, that picture of Cygnus X1. This is what it would look like if we had a star disrupt. If a star and a black hole were orbiting each other, like we expect that they do, because we see evidence for them, the star loses its matter onto the black hole, and we see all this shiny X-ray material come out. It's just a beautiful movie of what one of our expectations of black holes acting in the universe. I found that like Google. Google's powerful. So here's another image. This is real data. You can tell because it's not as pretty. Still good looking, not as pretty. So it's real. These are actual orbits of stars around our own cute little black hole. Look at that star. This is about the size of our solar system. This is in the middle of our own galaxy, Milky Way. And we have our own black hole about 4 million times the mass of our sun. And you can see these orbits are so tight, and there's nothing there, nothing shiny. That's our own black hole. So this is some of the best evidence around for our black hole. Okay, so we want to get to Laura Cadenati's portion of this tag team event. So I'm going to end with the last couple of slides about what I do for a living, which is I take 2 black holes and collide them because one just isn't enough. So I take that star that was shedding its material in the beautiful image, and now I put it as a black hole as well. So I have 2 black holes orbiting each other, and their fate is to merge into a single black hole. And when they do that, they're giving off a lot of radiation, but nothing that we can see. It's not electromagnetic radiation. It's something called gravitational waves, which Laura will tell us about next. So what this is a fake star field, because that's just too pretty to be real data, apparently. But the gravitational waves, these beautiful white lines coming out of these 2 objects, are the gravitational waves that we actually find when we solve Einstein's equations. The problem with Einstein's equation, same image, different star background on different colors, but you'll see the gravitational waves come out in a second. The Einstein's equations, I told you, G mu nu equals T mu nu, seem so simple, but they're super hard, and even the 2-body problem can't be solved, pen and paper, because it's nonlinear. So you can't just take one solution, Schwarzschild black hole, add a second Schwarzschild black hole, and get, bing, 2 black holes. No, nonlinear doesn't work, and instead you take 20 years and all the supercomputers you can get your hands on to create this solution. And this is what it looks like at the end of the day. This is the gravitational wave signal in time that Laura Cadenati is going to talk about with what we're trying to detect today. So instead of, this is my favorite magazine cover ever, because we're always like doomsday devices. When black holes collide, they're slingshot on a frantic deep space journey. Why are the black holes frantic? I don't know. I love this kind of stuff. It's great. But now we're going to switch gears, and you'll hear about gravitational waves. So we'll take questions at the end, if you guys don't mind. How long is that? I'll dance now. Ed will perform for us while we switch microphone. That'd be awesome. How much would I have to pay you?
Is it
It's ready.
where?
You're funny.
Oh, okay.
Like literally. I should have put it on that slide. Sorry about that. There you go.
Okay, good. All right, so it's going to be hard to follow Deirdre's act, so I'll be much calmer. I'll be staying here. So what I want to do now is to talk you more about gravitational waves, which I call here Einstein's Messengers, and why we're trying to detect them, and how, and possibly when. So this is an image from the Hubble Telescope. This is a very high-resolution image of the universe, and that's probably what you think about when you think about the universe out there. Is there a pointer? So there are galaxies, there are stars, it's out there, and you can see it. The image of the universe that instead Einstein gives us is something a little bit different. It looks more like this. So general relativity explains gravitation in terms of distortions of space and times. And we can picture the universe like lying on a grid, and big masses, what they do is to distort the space-time. And so, for instance, if you have a neutron star or a heavy object, it bends, it curves space-time like this. This could be the sun. This down here is a funnel that what a black hole would be. It's a mathematical solution that looks at how, what's the shape of spacetime, of this grid of spacetime where we found our coordinates. Whenever something catastrophic happens in the universe, so when two black holes collide, like you saw in the simulations that Deirdre showed earlier, what happens is that all of this is perturbed. Just like when you throw rocks in the water and the surface of the water makes waves, the same thing happens to spacetime. When you have big explosions, you have a supernova, you have a collision of black holes or neutron stars, the result is that we have ripples in space-time, and these ripples, according to Einstein, travel all the way to us at the speed of light. So what we're trying to do is to find on Earth the echo of whatever happened out there when catastrophic events happened, going all the way to the Big Bang. So this is another simulation that's similar to the ones that Deirdre showed you earlier. What I'm going to show you now is one of these calculations of the gravitational waves that are produced by the collision of two black holes. But what you're going to see with it is what kind of sounds these gravitational waves make. So we can, this wave, like everything else, we can plug into a speaker, we can listen to it, and if we can find them, we can hear the sound of colliding black holes or exploding supernovae. So in particular, when we go after, when we're looking at collisions of black holes, if the audio works, this is what we would hear. So we can now think about having a new way of observing the universe that uses a different type of messengers, gravitational waves. Everything we know so far is coming from electromagnetic waves. Gravitational waves are going to tell us something else. They're going to tell us things that we cannot see. So what happens when two black holes collide? What happens inside a core collapse supernova? So in a way, really, once we can measure these waves, we're going to have a new sense to perceive the universe around us. And so we're going to be able to combine electromagnetic waves and gravitational waves and get a new perception of the reality of the universe. So what can we learn about the universe? So there is a lot of things that we can go after. Because they're an entirely new way to probe the nature of the universe, they're coming from the motion of big masses as opposed to electromagnetic radiation, which is coming from the motion of charges. And so we can do, once we discover them, we can do some physics. We can answer questions such as, is general relativity the correct theory of gravity? Maybe Einstein was not right after all. We just have not been able to disprove him. How does the matter behave in extreme gravity conditions? So what really happens inside a black hole? Are black holes really the black holes of general relativity? What we have so far are mathematical solution of nasty equations, but what's really happening inside? What's the matter doing? We can do astrophysics and astronomy. We can go after questions such as what's powering the Gammaray Burst, those flashes of gamma rays that are being observed. And they are the brightest events in the universe. How do stars explode? How many black holes are there in the universe? Do intermediate mass black holes even exist? How many are there? And we can do cosmology. Can we go after the residue of gravitational wave that's still rippling out there from the Big Bang? So this is a plethora of physics and astrophysics and cosmology, all questions that are still unsolved, and that once we detect gravitational wave, we can go after. So that's why we are excited about measuring them. Now, how do we detect gravitational waves? So general relativity is a geometry theory, and physically, the way we can go after them is by looking at strains, so changes in length relative to the length itself, delta L over L. So a way that we can go after measuring them here on Earth is by taking the arms of, think about this as a clock and the two arms of it. As the gravitational wave is coming towards the screen, after a quarter of the period of the wave, this circle is going to have stretched into an oval. After another quarter of a circle, it's going to go back to a circle itself, then stretch in the opposite direction, and so on. So because general relativity is about the geometry of space and time, gravitational wave stretches and squeezes space-time. So if we can measure the changes in length in one direction and in the other as the gravitational wave comes through, then we can go after the gravitational wave itself. Easy, right? Okay. Now, the challenge here is that the gravitational wave is a wave. It's propagating into a medium. The medium is a space-time. And space-time is really, really stiff. So a tiny, tiny wave can carry a lot of energy. So there is a lot of energy that's producing these big catastrophic events that are astrophysics are happening out there. But the changes are really small once they reach us. So we had to be creative into how to go after measuring these changes. And so that's where the project that I'm working on, LIGO, the Laser Interferometer Gravitational Wave Observatory, enters the game. So I'm going to show you a little animation of, it's a very simplified cartoon of the principle under which LIGO works. So I'm going to start it. I can't use this. OK, so the idea is that we have a laser beam that gets split at a semi-reflective mirror, travels along two arms that are perpendicular to each other. They get reflected, they come back, and they recombine. But things are aligned in such a way that the interference of the two recombined beams is destructive. So the two cancel each other. Okay? So this is how the experiment is set up. Now, as the gravitational wave comes through, what happens is that the two arms are stretching and squeezing, like in the cartoon I showed before. And so as the gravitational wave comes through, one arm becomes longer, the other shorter, and so on with the period of the wave. And so the interference pattern changes, and so we get some light coming out. And we put a photodetector here to see how much light is coming out. Okay? So if we can build a detector that's so accurate that nothing else disturbs the measurement, then we can measure the passage of a gravitational wave. Okay, so that's the principle. Still easy? Okay. Now, I told you these things are very small, so this is the challenge. For the type of astrophysical sources that we're going after, so the collision of two neutron stars or two black holes, the kind of signal that we can hope to see, just because these things are so weak, is of a delta L over L of a strain of 10 to the minus 22. Now, that's a really small number. Okay? This is equivalent of measuring the distance between Earth and the closest star by the resolution of the width of an air. So that's how small this effect is. The resolution of our detector, so our detector cannot be as long as the distance between us and Proxima Centauri. If we want to build something on Earth, it can be kilometer scale long. And so we need to be able to measure distances that are of the order of 1 in 10,000 times the size of a proton. So that's the accuracy at which we're going. This train, so this kind of length is points, I guess these are, how many zeros are in here? I can't even count them. So this is a very accurate measurement that if you want to be able to do, it's very challenging because we need to fight against everything else that wants to change and move those mirrors more than gravitational wave does. Okay, so that's why LIGO is such a difficult experiment. So this project has been going on for a few years now. There are now 2 detectors that are operating, a part of the LIGO project. So one is in Washington State, and the other one is closer to here. It's in Louisiana. And the 2 are separated by 3,000 kilometers. And that means that a gravitational wave travels from here to here. At most, it takes 10 milliseconds. So that's how long it takes to go along a great circle. It's the National Science Foundation project. The construction started now 20 years ago. And the operation started in 2002, so we've been taking data for 8 years, and then we stopped for upgrades. We are now part of a large collaboration that has about 1,000 members. So it's a large community, 8 institutions, Georgia Tech being one of them, across 16 countries. So this is really worldwide efforts. And we are actually not the only project like this. There is also, we are collaborating with a project in Italy that's called Virgo. There are plans to build a detector in India, and there is an ongoing project going on in Kagra. So this is a worldwide quest, different projects, different experiments, and together we are aiming at detecting the gravitational waves to solve those physics and astrophysics questions that I mentioned earlier. This is what the data looks like. So this is data from the first run. So this was acquired 5 years ago. This is the kind of data that we have is as a function of frequency. So this is the audio band between 100 hertz and a kilohertz. This is the amplitude spectral density. And what we need to do is to do data analysis to find the signatures, the signals that are due to core collapse supernovae. So this is what a signal from a core collapse supernova will look like from mergers of neutron stars or black holes, echoes from the Big Bang, or the rotation of pulsars. So lots of what we do is to really dig through the data to find the type of signal that's left by sources that are in the galaxy or all the way out to cosmological distances. Just some pictures. What I showed you was a really simple cartoon. In reality, the experiment is much more complex. There is this is where the laser is. We have a complicated system of optics to clean the modes of the laser. This is the semi-reflective mirror. And then the arms are actually 4 kilometers long. You have some pictures. This is the mirrors. These are suspended. These are seismic isolation to protect from the motion of the ground. The real trick of the game here is to isolate our signal, isolate the mirrors, because motion of the Earth, vibrations, and other type of noise also want to move the mirror. So we have to be really careful at canceling and correcting the noise. So that's what LIGO looks like. Now, when can we expect to find gravitational waves? Well, this is just some simple scaling. So if we consider the signal from the collision of 2 neutron stars, so that's the one that we understand better. Well, 2 neutron stars, according to the theory, this type of coalescence happens once every 10,000 years per galaxy. Okay, so in our galaxy, we have to wait quite a bit to have one of these events happening nearby. So this is Earth. This is where we sit inside the galaxy. This is where the galaxy sits inside the range that was visible to initial LIGO. So up to 5 years ago, we were sensitive to gravitational wave from 100 galaxies. And we didn't really see anything, but that was not too surprising because the initial LIGO run was more to prove that we could do this. Now, in the current configuration, which we call the advanced LIGO, we can actually reach out to 100,000 galaxies. So this is the reach of advanced LIGO. This is what we are probing as I speak. So this data run has just started this past September. And we are now observing and acquiring data from most of the visible universe. We are expecting the detection rate, which is on the order of 1 event per month, once advanced LIGO is at full sensitivity. So we are really now on the brink of acquiring data that, according to the prediction, will yield the first gravitational wave signals. This is just to show you that, this is, right now, we're in this first data taking. We are acquiring 3 months of data. We're going to be do another run next year, 1 year later, and so on. And in 2019, we're going to have a full network of gravitational wave detectors where, just like with the GPS, we can actually triangulate and identify where is the origin of our signal. So the ultimate goal here is to combine the signal from gravitational waves, neutrinos, and photons, which are the messengers from electromagnetic waves, to really get a complete picture of what's happening out there. So this image is the image of a gamma-ray burst. It's thought that this kind of event is due to the collision of a neutron star with a black hole. So a neutron star that's eaten up by a black hole and is producing these big flashes of gamma rays. It produces neutrinos, it produces photons, and it produces gravitational waves. So in this new configuration, we're now going to be sitting here on Earth with 1, 2, 3 detectors. So this is the 2 LIGO, and this is the Virgo. And then we can, this detector really sit there like big ears. They're just waiting for something to come. And then if we can triangulate between the arrival time at 1, 2, and 3 detectors, we can reconstruct where the event was produced, send information out to satellites and to telescopes who are going to do a follow-up in the electromagnetic sector. And so we're going to be able to combine the electromagnetic waves, the gravitational waves, to get the full picture. And so we have established all this, connection with observatories to do this with our first data. So in brief, so LIGO has now resumed the search for gravitational wave just this past September. We have now fresh data. We are very excited analyzing it, understanding it, bonifying it, and who knows, maybe we'll be able to announce in not too long that we have detected gravitational waves. So stay tuned. Hopefully we can come back and talk about the results soon, in the spring. Who knows? Thank you.
We have time for questions. If you have a question, just raise your hand. I'll bring the microphone to you so everyone can hear your question.
How quickly do gravitational waves travel?
Excuse me. They travel at the speed of light. So yes, see. In fact, that's one of the things that, if that were not true, that would be a test of general relativity. So it's one of the things that we want to make sure is true.
Why do they travel at the speed of light?
Oh, that's for her.
Does that. Somehow it becomes my question if she doesn't like it. Basically because if you assume that it's massless like a photon, it travels at the same speed as the photon, but it's basically a spin-weighted field of something crazy. Let's ask the dean. Where is the next person?
Question?
Yeah, over
A
here.
hand over here somewhere.
As neutrinos are emitted by a supernova, are they subject to black hole gravitational pull?
Are they subject? Sorry.
Are they sucked in by a black hole like photons are?
So the neutrinos are emitted in the first stages of the collapse, so they can escape. I mean, it's just emitted in the first stage before the protoneutron star is formed. So we get to see that signal even though there is a black hole left behind.
Okay, but theoretically speaking, if they crossed a black hole's event horizon, would they be affected? Or?
I guess yes, they would be. But in the core collapse, they escape before the black hole is produced.
If a gravitational wave was, say, discovered tomorrow, what would be the biggest implication on us?
Somebody will
Einstein's
get a Nobel
equations,
Prize.
The Nobel
Well,
Prize.
I mean, it's so I think the most likely sources of gravitational waves are going to be the collision of a neutron star, superneutron star, and the black hole or two black holes. So what that would do is to open a better understanding into the astrophysics of these sources, so a better understanding of the population, so how many black holes there are. Lots of these projections are based on the observation of one or two systems, so lots of the astronomy is based on just a few examples. So it would just give this additional information to start decoding the physics of it. Now, if we can actually decode the signal, what I've not been talking so much about, in these waveforms that are produced that Deirdre also showed, little wiggles or little changes in the waveform shape itself are associated to the physics of the event itself. So we could be able to understand better the equation of states of the neutron stars, for instance, and that would give us some clue into nuclear physics also on the ground-based, on the Earth-based scale. So there could be consequences also for nuclear physics, but that would have to have more than one. So the first thing is the astrophysics.
It would rock our world. And it would be career opportunities for everyone. Sorry, just kidding.
Do these waves lose amplitude or strength with distance travel from source to LIGO? For instance, Hubble photos show at least 100 billion galaxies out there when we reach their extents, and you're measuring 100,000 with the advance. Being able to see these waves as we see the photons from Hubble, will you give you more examples, more chances to see these waves?
So these events are pretty rare, right? So what I was showing is that LIGO is kind of now spanning order of 100,000 galaxies, and in each of them there could be one event in 10,000 years. So we're talking about 1 or 2 events per month.
That's why I asked for those
right.
100 billion measurements. Will they have strength when they get here from the further reaches of the universe?
I'm sorry.
Strength. So they do
Yes.
it.
Can you measure them? They still have amplitude, or will they fade like photons?
They propagate, okay, so I understand. So what we measure is the amplitude of the strain itself, so it kind of scales down like 1/r, right? So that's the extent of the scale. So if we can get 10 times more sensitive, we can get 1,000 times more volume. So it's a 1/r spreading. It's really like with photons, yes.
Get to them faster, maybe. I need the workout.
Just thank you.
Does this help us understand dark matter and dark energy, or is it just totally unrelated?
This is fun.
You want to take that?
Me? That's pretty unrelated.
Yeah.
I mean, let's imagine that we don't detect a gravitational wave, or you do, and it doesn't come out with the speed of light, or there's an extra polarization. Then it might make a difference, right? Because then you'd say general relativity is not the right theory of gravity. And now you've opened up to Vista to start explaining dark energy. If it comes in and nothing's unexpected, then we're really doing astrophysics.
But I think the first measurements are going to be of the, kind of from the close-by universe. We're going to start from 1 or 2 events. So I think once we get bigger detectors, more sensitivity, at that point we can do this kind of studies with higher rates of events and population understanding.
Okay, the LIGO array was a pair of arms where 2 light waves meet and then they cancel each other out. Is there any benefit to reflecting them around back and forth before you join them again?
Oh, yes, I actually do. We actually do that. I gave you the simpler cartoon where they travel back and forth, but we actually do, the bouncing back and forth is about 100 times. So yes, we do that. And that's to amplify the power in the cavity, and the more power you have, the more photons you have in the system, and so it reduces the shot noise, so it's all related.
Oh, okay. You talked about the formation of black holes through stellar collapse. What about supermassive black holes?
Yeah, I skipped those. Not because I don't love them, because I do. So supermassive black holes are harder to explain their formation. It's one of the big challenges in astrophysics right now. And actually, we have a lot of people working on that also in the center. But you can imagine supermassive black holes would grow from very early on in the universe. They would grow through mergers. They'd grow from accretion. They would form in like the early dark matter pockets that happen after the universe is expanding, and they just keep growing, and they form at the center of galaxies that way. They collide as well, potentially, if two galaxies collide. They're so massive that LIGO won't detect them. They're a different frequency. We wouldn't be able to hear them like we did those gravitational waves. If a space-based mission gets launched like LISA or ELISA, that's the black holes we would be looking for. Supermassive black holes colliding, those we can see all the way out, like really early on. In the universe, we'd be able to detect them.
Does the moving of Earth through space and the solar system affect your ability to detect this stuff because of the changing gravitational forces on the Earth itself?
That's a small effect compared to other noise sources that we have, actually. The Newtonian gradient is actually not one of the major effects. The biggest source of trouble for us is actually seismic motion. It's the fact that the detector is sitting on Earth, and the Earth is moving on jello. So it's, that those seismic motions are the biggest problem, and that's why lots of the engineering has gone into seismic isolations, for instance, and understanding, there is lots of feedback loop and really lots of engineering into designing something that's stable against vibration and seismic motions.
Do we have a last question over there, Deirdre?
Yeah, I'm just running between the aisles for fun. Sorry.
Thank you. If there's so much trouble with seismic motion, would it be easier to send it into space?
Right, so that would be LISA. Actually, this is another project that has been in the works for many years. I think the current plan is to send it to space in 2025 or 25, right?
We need money. Let's put the hat around.
So once you're out in space, you don't have the problem of seismic motion, and the idea is also that you can put, the mirrors are actually standing in spaceships, and so you can put them very far apart from each other. And so that's why LISA is going to be sensitive to much smaller frequencies and go after supermassive black holes. So it's going to be doing a different type of astrophysics. That's actually part of what was challenging in LIGO, that we know about supermassive black holes, but the black holes that we are after are smaller, and we don't know as much about them. So it's really, LIGO has really been in the spirit of exploration of a little bit of the unknown, because we don't know so much about the sources that we're going after. LISA is going to be doing a different type of physics, and it's going to benefit from not having seismic motion.
Their noise is somebody else's source. Like their noise is literally like gravitational waves from white dwarfs colliding. It's pretty amazing.
All right, well, let's thank our speakers one last time. And yes, this is a good one. If you have questions, you can come down at the front afterwards. Thank you.